Okay, so welcome back. In today's videos, we're just going to go ahead and prove some properties related to our OLS estimator. And well, you might be interested in this part if you wanted to take some econometrics exam. But if that is not the case, and it's totally okay to just skip this video. All right, without further ado, the first thing we want to prove is called actually unbiasedness of our OLS estimator. So to prove that OLS is an unbiased estimator, essentially what we want to prove is actually the expectation, the conditional expectation of our OLS is equal to the true value beta. So this is something we kind of already done in the simple regression model. So remember, like we just need to substitute this beta with our expression. So for our multivariate, it is okay. I will just write it again. Well, it's quite tedious, but anyway. Dot y and on the condition of x. So here we're gonna view x as some constant. Okay, and remember, like our assumption is all about our error term mu. So we also need to substitute this y with another expression, which is the expectation of this part. Let me write this again. And y is actually equal to x dot beta plus mu. Okay. Condition sign, and I'm sorry. So this thing's going to be equal. So if we try to expand the parentheses, and we're going to have the expectation of the first term, which is xt dot t transpose dot x matrix dot beta on condition of x. So this term, so if we take a look at this first part and the second part, we notice that it's just the inverse of the second part. So a matrix dot its own inverse. It's just going to be some identity matrix. And then beta dot I is just going to be beta itself. And expectation of beta is just going to be beta. So we're going to have beta plus. So this part dot mu is going to, well, remember x here is some constant. So we can actually take that out. So it becomes, we just put that out of the expectation. So it's become, all right. Dot the expectation of mu, the vector mu, on the condition of x. So we've seen this many times. So we know based on the OLS assumption, this expectation of error term, of course, is going to equal to 0. So the whole expectation will equal to beta. So we now just proved that the beta is an unbiased estimator. Cool. So next, what we're going to prove is called consistency. Okay, consistency. So to prove consistency, that is actually to prove the probability limits of our OLS estimator, beta hat, actually goes to beta when n goes to infinity. So in other words, if we have a large enough sample, then our estimator will just converges to the true value beta. In other words, our beta hat is going to be consistent. Okay, to do that, we also going to need to substitute beta. And we already have the expression for beta right here, so we're just going to use that. So the probability limits of beta hat is just going to be equal to this expression. Okay. Let me write that again. Dot the mu. So we now know that if we take the probability limits of beta is a constant, so it's still going to be itself. And the problem is become the probability limits of the second term. Okay. So let me write it here. So we kind of want to prove that this term actually goes to 0. So the consistency will be proved. So how to prove that? We kind of wanted to construct something with n over 1. And why is that? Well, because it's always going to be useful if we met some limit problem if we have some 1 over n. So let's try if we can do that. So how about let's times n for the first part, and then dot 1 over n for the second part. And because we know for the second part, it's essentially just going to be some matrix, okay, dot mu. So it's just going to be some, let's say, the row vector is actually going to be, I say this is x1i and x2i, all the way to xki, okay, dot our mu. So essentially, this is just going to be some dot products, x1i dot mu, x2i dot mu, x and ki dot mu. And this is just going to be, in other words, like dot products can always be written in the sum form. Okay, just some sum, okay. And also if we times 1 over n, this form somehow, well, it should already ring a bell at this point, because we know the law of large number, okay? The law of large number. Let's go to this page. What the law of large number says is, so if we have a variable x, and if we take the average, which is 1 over n times the sum of x, and if n goes to infinity, then this whole thing will converges in probability to its expectation. All right. And I know that there are many other different variations for law of large number, and this is just some very basic expression. So then if we look at this second term here, this form exactly matches the law of large number. So we can just apply the law of large number. So now we're going to have beta plus probability limits of the first term. And again, if we kind of put the n inside this inverse, then what we're going to have is 1 over n times x inverse times x transpose times x. The whole thing takes inverse. And the probability limits of 1 over n. Well, this part exactly goes to its expectation, which is x transpose dot mu. Again, based on our OLS assumption, since each individual variable x should have no correlation with our error term mu, so this term will also goes to 0. And also this term, well, essentially it is also some, if we try to find out each element, it's also going to be some sum of x, right? So this is sum x2i. So x1i and x2i, blah, 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 blah. So if we also times 1 over n, essentially it's just going to be some matrix that converges to some number. It's not going to go explode at some point. So let's assume it also going to converges to a different matrix. Let's say it's omega. So we take inverse, and it's just going to be omega inverse, sigma inverse, I'm sorry. So essentially what's going to be left is beta plus the sigma inverse dot 0. And of course, this thing is just going to be equal to beta when n goes to infinity. Okay, cool. So we also proved the consistency. And finally, what we need to prove is something called efficiency. Okay, efficiency. And also, by efficiency, I mean we just need to prove the variance of our OLS estimator is the smallest variance, okay, among all other linear estimator, okay. So in order to prove that, we need to first assume that there are some linear estimator, let's say beta tilde, which is equal to some matrix C dot our vector y, because this is also some kind of linear transformation, right? Because our OLS is also satisfy this form, because it's, let me write this again, okay. Dot y vector. So our OLS estimator is essentially also some kind of linear transformation of vector y. So let's just assume we have another beta tilde. It's also an unbiased estimator, and this is also unbiased, okay? Unbiased estimator, which means we have the expectation of beta tilde, which is expectation of C dot y. Okay, so let's also substitute y, then we have expectation of C dot x dot beta plus C dot mu. And this thing should be equal to beta. All right. And now we know that since C and x and beta are all constant, so we can just put them out. It's going to be C dot x dot beta plus, again, C can be, taken out of the expectation, C dot expectation of mu. And this thing will goes to 0, of course, because expectation of mu, right? And essentially what this suggests is C dot x dot b, it's just going to be equal to beta. In other words, C dot x going to equal to some identity matrix of k times k. Well, these results will come in handy in the later proving process. All right, so now essentially what we want to compare is the variance of our beta hat, OLS beta hat, and the variance of our beta tilde. Okay, to do that, we first need to find out what's the variance of our OLS beta. And by the way, let me actually introduce some variance rule to how to take variance of some matrix. Let's say we have a matrix A dot some variable x, and these things will equal to A dot variance x dot A transpose. Again, this is something that you should learn in the linear algebra, so I'm not going to get into details here. So now if we look at the OLS variance, we know that the variance of beta hat is equal, like beta plus this whole thing, let me write it again, dot mu. And we know that the beta is a constant, and the constant will have no contribution to variance, so it just disappears. Then for the second part, we sort of apply this rule. Then what we're going to have is it's just going to be equal to, okay, the inverse dot x transpose dot variance of mu dot the inverse of this whole thing. And what is the inverse of this whole thing? Remember, like if A dot B take inverse, it's just going to be B transpose. I'm sorry, it's transpose dot A transpose. Then if we apply this to this part, then it's just going to become x dot this part. Cool. And since the variance of our mu, based on the assumption we know it's going to be a scalar, it's just going to be sigma square, right? So the whole thing is just becomes sigma square dot, okay, let me write it for real quick, dot T transpose dot X dot, all right. So just by observation, we find that this is actually the inverse of these things. And these two things will got cancelled out. So finally, what we have is, well, actually, let me adjust my camera. What we're going to have is only sigma square dot our X transpose dot X takes inverse. All right, this is for our variance of beta hat. And in the same manner, we're going to, let's go to a different page. So in the same manner, the variance of our beta tilde is just going to be equal to, remember the beta tilde is variance of C dot X dot beta plus C dot mu. And in the same manner, so like C dot X dot beta is constant, and we can drop that, and what we're going to be left is C dot variance mu dot C transpose. And that's going to be the sigma square dot C transpose. Right now, what we need to do is just to compare these two, like the variance of beta hat and beta tilde. And let's say we're using this we're using this variance of beta tilde, subtract the variance of our beta OLS. Then what we're going to have is actually the sigma square dot C transpose minus the sigma square dot X transpose X take inverse. So now we're going to use some mathematical tricks. Remember in the previous videos we introduced like the I identity matrix is actually going to be equal to the projection matrix Px plus the M matrix Mx. Okay. So then if we kind of inserting this I matrix between this C and C transpose, because essentially it's still going to be the same, right? Dot. And minus this part. Okay, I'm going to draw a circle to represent this part, okay, to save some work. And then what we're going to have is the sigma square dot C dot P matrix plus M matrix dot T transpose. And then what we're going to have is sigma square minus this circle dot C transpose plus sigma square dot C dot M dot C transpose minus the square, the circle. And what is P? Remember, the P is actually going to be equal to C dot X dot, okay, let me write this for real quick, minus an X transpose dot C transpose. And some interesting thing just happened. Because remember, in the previous page, we just proved that, because this is an unbiased estimator that suggests C matrix dot X matrix is going to be equal to some identity matrix. So if we apply this here, then this thing will just going to be equal to some identity matrix, and so will this part, identity matrix. Okay, so the whole thing is just become sigma square dot X transpose dot X plus the sigma square C dot M dot C transpose minus, remember the circle is also the sigma square dot X. So like now what is happening? The first term and the third term just got cancelled out. What is only going to be left is only our sigma square dot C dot M matrix dot C transpose. And again, here's some some linear algebra knowledge, because we know the M matrix is actually well, this whole thing dot m is actually positive semi-definite, which means if we times the sigma, these things should always greater than or equal to 0. So this is always a positive number. The variance of beta tilde is always going to be greater than the variance of our OLS estimator beta hat. OLS estimator is always going to be the smallest variance. Okay. It's always going to be smallest. Okay, so now I've proved the consistency, unbiasedness, consistency, and efficiency. In this video, I hope this can be helpful, and I'll see you in the next video.